Any questions about anything before we start? Yeah, Randy? No, I'm only up to Molnar. Well, if Pollock is 2, it goes Pollock, Sheely, Hamami, or no, Chen, Hamami, okay, then So, Albanese, and Molnar, and yeah, so I don't know what happens after that. We'll see. Have you beaten it? Have you? Oh, yeah. See, the thing is, I'm sort of cheating. I started a game and I left it on. I left it going. You know, I just played a little while and left it going. And it's been up for 3 days. What's that? I was actually the first person to beat it. Just gonna throw it out there. Okay. Yeah, and it's getting kind of cluttered.
On Stack Overflow, there's all these like AI conversations about like the optimal algorithm to play it with.
Mm-hmm.
And, like people can get like 60, whatever, 2 to the, I don't know, 14.
The highest you can get to the 17.
How?
You have to make a perfect snake, and the last block to pop up has to be a 4. You'll get, like,
oh yeah.
You'll get all, and then if a 2 pops up, you lose. 4 pops up, you just
Anyway. Okay, any other questions besides? Do you guys know what we're talking about? The EC version of 2048 with the professors' faces? Yeah. Even computer scientists know this?
You can't put anything past 2048. It just stops.
And also I saw this very clever variation on the game called Divided, where instead of multiplying powers of 2, you are finding between 2 integers that are not co-primed, they're GCD. So if you have 2 integers that are not co-primed that collide, then they merge into their GCD, right? And so your goal is to get down to 1. And this is due to Drew and company. I don't know. I'm assuming.
There's also a Fibonacci version that's really hard.
Yeah, that's interesting. Okay. Well, anyway, last time, remember, we were talking about, what were we talking about? Let's see. We pretty much wrapped up with the fitness proportional selection discussion. We were talking about Markov chains, GAs as Markov chains. And we talked about the quote-unquote experiments of Dijon and Spears. And this was on fitness proportional selection. And basically what this showed was something that we are not totally surprised at, that monomorphic populations have a lot of inertia. And if you use a fitness proportional selection with the GA, what that tends to do over time is go to a monomorphic population, hang out around there for a while, then bop off to another monomorphic population, hang out around there for a while, and so on, visiting them all infinitely often. Of course, you never see that happen in your lifetime or anything. But what it tends to do, it tends to linger around the monomorphic populations and transition between them. Okay, so anyway, what this means, for example, is that if you have, say, if all the strings have different fitnesses, the population with all copies of the highest fitness string, that's going to be both the highest average fitness population, it's also going to be monomorphic. You'd really love to have that population, but what happens is the genetic algorithm, maybe it'll spend time around there, but it'll also spend time around the monomorphic population with like the second highest fitness string in it, which is somehow worse for you if you're trying to solve a problem than the population that has, say, n-1 copies of the highest fitness string and one of the next highest fitness string. So anyway, if we alter the method of selection so that somehow we keep the best we've seen so far, then we're not going to see this sort of phenomenon where you lose a gain. So potentially, you quote unquote lose a good problem solution by sort of transitioning to a lower level or lower fitness monomorphic population. And thus, what you really want to do, if you want to get these things to work out for you, to solve your problems and whatever, is you're going to want, in some sense, to have a way of keeping the best you've seen so far at all times. So using some kind of elitist selection is what we want to do. So we need a way to, quote unquote, keep the best seen so far. So we don't sort of lose in this fashion by going off to a monomorphic population with second highest fitness rather than going off to a population with n-1 copies of the highest fitness string and so on. Okay, so that's the point. You want to keep the best you've seen so far. And the method for doing this is elitist selection of various kinds. We've talked about that very briefly. And let me just consider one quick example here. Say, for example, and this is only one example of elitist selection. There's the half-full elitist selection where you keep the best you've seen, and the half-empty version where you throw away the worst, whatever. But this is the elitist selection. Keep the top two strings in terms of fitness in P of t as members of P of t plus 1. And then choose the rest of P of t plus 1 using whatever, fitness proportional selection or whatever. All right, now let's look at this as a Markov chain and think about what's going on here. Remember yesterday or Tuesday's discussion, we talked about all these different versions if you have PC, PM, and all that. And let's assume, say, you have PC bigger than 0, PM bigger than 0 for the sake of argument. We saw that fitness proportional selection with positive crossover mutation probability, in fact, all you need is positive mutation probability, results in an irreducible Markov chain that visits every population infinitely often, right? But in this case, when you use this elitist selection, it's not going to be able to get away from populations that have, say, for example, 2 copies of the very best string in them. Because once you're in such a population, no matter how you choose the rest of population time t plus 1, P of t plus 1 is also going to be such a population. Vincent?
Can you mutate for 2 different strings?
No.
So those just immediately go on.
Yeah, as members of P of t plus 1, right. It's almost like seeding the population with those guys. In this case, as a Markov chain, view of the world, the set of populations containing 2 copies of a highest fitness string that set of populations is, in Markov chain language, a closed set of populations. It's a closed set of states for the Markov chain. And it's actually, if you assume PC and PM are positive, it's going to be a recurrence class because you can reach any one from any other. If you have, for example, a unique highest fitness string and PC and PM are bigger than 0. So generally, not always, it's actually a recurrence class for the Markov chain. And you can imagine when you're running this thing, you might do it keeping the top 2 for a while and then ratchet that up a little bit, keep the top 4 or something. You know, there's all kinds of variations on this. And if you go over to Hod Lipson's lab in MAE and CS, this is the kind of thing they do. They use elitist selection when they're solving all these wonderful problems for locomoting robots and discovering the laws of nature from data and all that kind of thing. So real life GA successes, success stories, how about? Just to be prosaic, why not? Are mostly about GAs that use elitist selection of various kinds. Not fitness proportional selection. But fitness proportional selection helps us understand how GAs work, which is why we like to talk about it. Now, one example, like I wanted Cameron to tell us this story, this cool story about, he told me, I'm not sure I understood it completely, but it's about laying out FPGAs using genetic algorithms. So would you care to share this with the class?
Sure. So I guess basically the way an FPGA works is you have a bunch of lookup tables that you can program a specific way to achieve a certain logic function. And I forgot the name of the researcher, but some researcher tried to program a genetic algorithm on his FPGA, and he wanted to generate a 1 kilohertz square wave signal. And he programmed some fitness function, and he's actually able to generate this 1 kilohertz square wave. But the issue was the circuits were laid out in a way that no human could have possibly laid out themselves from scratch. For example, it had signals that drove logic blocks that were just never used. And so if you tried to take the design and replicate it in a way that humans would have ordinarily designed, it didn't work. Tried to take and move it to a different part of the FPGA, it didn't work. They said the way this algorithm evolved was designed in a way that we just had too many effects we couldn't understand. There was, this loading on the power supply on the clock, and it got that basically able to get this one configuration that worked. If you ran it again, you can get other configuration that worked, but he could never replicate it himself just by designing it using regular design principles.
And so the fitness function was sort of like, how good something kilohertz square wave is this that's coming out, right?
Right.
So it's essentially an analog function. What they're doing is they're matching the approximation of the square wave that comes out from a certain layout with an ideal one, right? And then they reconfigure a little bit and hope they get a better square wave. And part of this reconfiguration involves things that don't get used in the logic of the system at all, but are there and have fields and all that kind of garbage, all that kind of analog stuff going on, which helps the square wave be better, right? Is that the correct understanding of what's going on? So when he says no human could possibly, well, clearly a human did design it, right? But indirectly, but yeah, I think that's kind of a cool thing, and that's actually what happens with a lot of GAs. And if you know, in the early days of genetic algorithms, people were always saying, oh, well, we really don't know how they work, we really don't understand how they work, but they do sometimes, whatever, and so we're going to use them. And you know, there were higher hopes than there are now, but still, they're useful, and they're especially useful for situations where you have a natural kind of way of thinking of your search space, your phenotype space as, you know, encodable by genotypes of various kinds. Okay, so anyway, what I want to talk about briefly now, this is the last thing we're going to talk about before we talk about the game theory stuff, is this no free lunch theorem from optimization theory and what it may or may not have to do with genetic algorithms. So here's one more item, and this is the so-called no free lunch theorem of two guys who came up with this were David Wolpert and William McCready. And they actually published their paper in the Volume 1, Number 1, the very first issue of the IEEE Transactions on Evolutionary Computation. Okay. Even though it's not clear, as you'll see, exactly what it has to do with evolutionary computation or genetic algorithms. Okay, so the idea here is the following. You take this multi-purpose algorithm view of the world. So if you're given the idea of a multi-purpose algorithm, and we've alluded to this before in the context of Goldberg stuff, So it's something in a box, right, that you maybe you buy off the shelf or whatever, and you have some fixed search space S, okay, and you have a fixed way of searching, which can be a recursive description of an algorithm, say. You know, if I see this up to this time, then do this. You know, it doesn't have to be I go from point A to point B to point C and all that in S. And also an initialization. Okay, so this is your MPA. And your goal in life is to use your MPA, and this is going to look vaguely familiar because of our discussion of Goldberg stuff. Use this MPA to maximize a variety of functions f from the search space S into the reals. So we think of these things as like objective functions, fitness functions, or whatever, and we want to search around in S and find a high F item in S. What does the No Free Lunch Theorem say? The No Free Lunch Theorem says the following. Any such MPA, if you average its performance in maximizing F over all possible Fs, so the average performance and suitably defined, like for example the closeness to the max or whatever, the average performance of any MPA where the average is over all possible Fs from S to the reals is the same as the average performance of any other MPA over all possible Fs. So what does this mean? This says that no matter how clever your MPA builder is, the MPA is going to do better than average on some Fs and worse than average on others. Okay? So colloquially, this is the way people talk of it. Any MPA does, quote unquote, above average on some Fs and below average on others. There's no sort of silver bullet MPA that solves everything. I guess you could call it the no silver bullet theorem, might be a more accurate description of what it is, but they called it the no free lunch theorem, which is cool. Anyway, so that's the NFL theorem. Now, why did they publish this paper in volume 1, number 1 of the IEEE Transactions on Evolutionary Computation? Well, it was because Holland and Fogel and everybody, all the big GA backers, even though they were divided into different camps, some of them thought crossover was stupid, some of them didn't, all this kind of thing. They were trumpeting the usefulness of GAs as sort of universal fitness function maximizers, universal searchers, that kind of thing, in some sense, the kind of the Goldberg view of the world. And what Wolpert and McCready wanted to show was that's a little bit dangerous. It's like a warning shot across the bow, so to speak. And it's not exactly clear how the NFL theorem, the no free lunch theorem, applies to genetic algorithms. Let me explain what I mean by that. So how this theorem applies to GAs is not totally clear. Okay, so there's a really fundamental question. First fundamental question is, like, what is the search space S in a GA? Is it phenotype space phi? So, for example, in a GA, what is the quote-unquote search space S? Is it, and these are open, these are questions that don't have a single answer, by the way. There are things that you can answer in various ways depending on the kind of problem you're looking at. Is it phi, the phenotype space, the space of potential problem solutions, or is it P, script P, the set of all n-string populations? Because really your GA is evolving populations. It's moving from one point to another in population space. And in the No Free Lunch Theorem, the kinds of algorithms they're talking about, these multipurpose algorithms, are moving from one point to another in the search space. And it's hard for me to see how a GA is moving from one phenotype to another as time goes on, unless you define that to be the highest in the current population, whatever. But what I'm saying is this question does not have a really solid answer. Another thing is, technically, even though the No Free Lunch Theorem allows random stuff to be happening in algorithms, the No Free Lunch Theorem applies only to MPA's, multipurpose algorithms, that never revisit points in S that they've visited already. And clearly that's not a satisfactory kind of thing for GA, because if you run one for a really long time, then you see revisiting populations a lot, all that kind of thing. So those are two reasons, and there's one that I always forget that I want to throw in. No, that's it, I guess. Okay, I didn't. But anyway, despite the fact that it's not exactly clear how this theorem applies to GAs, it's still, like I said, it's like a warning shot. It's a kind of a cautionary tale about how not to expect too much stuff. And let me just give you a quick possible variation of the NFL theorem. Actually, two variations of the NFL theorem that apply more explicitly to GAs. So here are two possible variants on the NFL theorem, and I don't know whether they're true. I haven't sat down and tried to figure out proofs of them or anything like that. But here's one version. Here's one version. You have a box. Again, you have this box, and inside you have this box, fixed phi, phenotype space, fixed encoding G, and fixed sort of genetic operators and selection method. And that's this. Let's call this the MPA. Could call it the MGA, whatever. But anyway, your goal in life is to maximize a lot of different Fs. And the theorem, here's the proto-theorem or candidate theorem. The candidate theorem is that the MPA does better than average on some fitness functions F from phi to the reals, and worse on others. And that's a very qualitative statement. A tighter theorem would be something like averaged over all fitness functions, the performance of this is the same as any other performance, the performance of any other MPA. Okay, so that's one variant on the NFL theorem that would be, I think, an appropriate GA version of it. Now, what I want to do now, though, is I want to rotate that by 90 degrees in some sense. Because I think I've tried to sell you on the idea that the fitness function and the encoding have to sort of work together, right? They may have to make sense in terms of one another. So here's a rotate this by 90 degrees. Okay, so you have a fixed phi, and you have fixed genetic operators and selection method, and you have a fixed fitness function, f, from phi to the reals. Now, can anybody guess what the 90-degree rotation of this theorem is going to be? Paul? Yes, some encodings G for phi. So here's the candidate theorem. Some encodings G result in good performance on this particular f, say above average. Other G's do worse. They do below average. And a tighter, more quantitative version of the theorem would be if you averaged over all encodings, the best you could do on this particular f, you would get the same. Well, no, I don't want to try for a numerical version. Okay. So the moral of this whole story, the big point I'm trying to drive home is that the encoding and the fitness function need to, quote unquote, work well together. You can't expect to go to the store and buy a fixed MPA with a fixed encoding scheme and use it to maximize a lot of different Fs. You just can't. And you can't expect, if you're given an F, you can't expect to be able to just slop together an encoding and have a genetic algorithm that maximizes that F well. And if you read Mitchell's book, the reading assignment that's coming up is to read the last 2 chapters. She'll say, in sort of passing, she'll say, the one part of GAs that really hasn't been given as much attention as it should is the whole encoding part. Well, yeah, okay, that's what I've been trying to tell you. Now, the thing is, they have to work well together. So really, to risk offending people, you want to design your genetic algorithms intelligently. You want to design your genetic algorithms intelligently. You know, for a given fitness function, you're going to want a G that works well with it. On the other hand, you don't want to spend so much time doing this that you're always trying to put the ball on the opponent's 1-yard line before you even start. Okay, so you want to strike a happy medium. You don't want to spend too much time, quote unquote, rigging things to succeed. You want sort of a happy medium. Now, like those of you who've taken a class from me before have heard this joke, okay? It's not really a joke. Can you guess which one I'm going to tell? No, it's long ago for you. It's like 2 or 3 years ago. But, okay, what is the definition of a mathematician? A mathematician is someone who, when given a 10-minute problem, spends 5 minutes figuring out how to do it in 5 minutes, and then does it in 5 minutes. Okay? Got that? All right. So if you spend all this time rigging things to succeed, you're behaving like a mathematician, because you'll probably spend just as much time maximizing your F as you would if you just did it blindly. If you try to design this algorithm that does it. So anyway, that's the kind of thing you have to avoid. Okay, so that's about all I want to say about these GAs and stuff. And Now I'm going to hand you back your midterms, unless there are any other. Let me see, make sure there's nothing else I want to throw in here. Oh, yeah, there is, actually. Let me see what time it is. Yeah, there is one thing I want to throw in. One possible approach to doing the rigging.
What is after descending the from encoding results? Is that
Where are we?
can
Some encodings G result in above average. Other G's do below average. Okay. So here's a possible approach, which I think might be promising, and I haven't pursued it yet, but maybe the biologist in the class has heard of Price's theorem. Have you heard of Price's theorem from genetics? No? Okay. So one possible, what do they teach you guys nowadays? No, I'm just kidding. I would never presume to say what biologists teach. Okay. Okay, one possible approach to sort of designing sort of good fits between a fitness function f and an encoding g is based on this idea of Price's theorem from genetics. And I'm going to state it in a very rough fashion here. It basically says that, and we're talking about standard genetics with DNA, 4 nucleotides, and all that kind of stuff, you know, whatever. That if you have an observable, let me just, I might just copy it off a page. Okay. If what he called canonical observable, and that's just a fancy 2-word term for, say, the average fitness or height or whatever in our context. So if a canonical observable, I think I'm going to have to copy it down. I apologize for this. Of a bunch of parents. This, by the way, this doesn't have anything to do with selection. It has only to do with the genetic operation stuff. Has a high average positive or perhaps negative correlation with its value let me write it out completely, with the same canonical observables. Value on the children to which these parents give rise. And of course there's a lot of randomness in the way that parents give rise to children. There's crossover, there's whatever. And this theorem referred to this particular kind of thing that we see in biology. Parents give rise. And that's all part of the if part of the theorem. Then we will tend to see that canonical observable increase or decrease in the case of a negative correlation over time from generation to generation. According to whether the correlation is positive or negative. So if it's positive correlation of the value between the parents and the kids, then it tends to increase over time, over generations. If negative, then decrease. And this makes a lot of sense because, you know, like, of course there's no selection here, but the point is that if you're, say, if all your parents have a certain height, say, and that the value of that trait has high expected positive correlation, you know, and of course it takes into account all the randomness of reproduction with the whole possible sets of children that those parents could give rise to, you would expect somehow that to kind of have some momentum in over time for populations. Now, what does this have to do? Why am I thinking this might be a possible approach to designing good fit between F and G? Well, if you can design your G so that using these standard genetic operators and whatever, you have a high positive correlation on the average between the value of your fitness on a set of parents and your value of fitness on a set of children to which they give rise, then maybe that'll give it some pressure to increase over time. So the possible use of this would be to, say, given F, you design your G so that am I hearing that, or is that actually coming? Is that actually happening? A phone, my phone, maybe. No, it's someone else's phone? I'm hearing it. You heard it too? Okay, thank you. I was really afraid. I mean, it's just been a long, like, 15 or so hours. Possible use. Given F, design G so that the value of F, average value of F over a bunch of parents, correlates positively with the average value of F over their possible children. And that's something you could just look at sort of one genetic step, the step that takes parents to children. We're not talking about selection here at all. We're just talking about, and hope that maybe if you get a price-worthy FG match, or G, then things are going to work out. So that's one idea I think might be in the cards, but, you know, I don't think anyone's really tried to do that. Okay. So let's take the break now, and let me hand back some midterms. And I know a lot of your names, but I don't know a lot of your names, so please pardon me if I don't know your name. The expected value starting from state 1 of the total number of times you hit N11 is going to be infinity if you hit state 11 with positive probability from state 1, which you do because 1 goes to 2 and 2 goes to 7, and 7 is in the same recurrence class with 11. Okay. Third bullet. With probability 1, N7 starting from 1 is equal to infinity. No, not necessarily. No, not at all, because we know that 1 goes to 3 with positive probability. Therefore, it's not true with probability 1 that you're going to even hit 7. So with some positive probability, prob 1 N7 equals 0 is going to happen. Okay. Okay, R15 less than R13. Let's see. Well, R13 is equal to 1/5, and that's the probability that starting from 1 you end up in the little recurrence class, right? And R15, state 5 is in that recurrence class. The probability that you end up in there is the same probability, the same as the probability that starting from 1 you hit any of the states in there. If you end up in that recurrence class with probability R13, R13 equals R14 equals R15, bottom line, okay? So there's, now R17 equals 4/5, that's true because that's the probability that you end up in the big recurrence class starting from 1. And I told you that the probability you ended up in the little recurrence class starting from 1, which is the same as R13, is 1/5. And that has to be 1 minus that. And then for every j, that ratio converges as n goes to infinity with probability 1. It does converge with probability 1 for every state j. It might converge to 0, it might converge to something positive, whatever. But it converges to different things for each j.
Is that true then?
That is,
For every state j?
yes, it's true that for every state j, the total number of fractions of time you visit state j, the limiting fraction of times you visit state j converges to something. Okay? And it's either going to converge to 1 over mj or rij or mj or whatever, you know, like that kind of thing. 1 over mj, actually, or 0. Given that you start in state 3, this is the next bullet, the limit of n5 of n is finite and non-zero with probability 1. Yes, because you're in a finite recurrence class. Therefore, every guy there has a positive mj that's, a finite mj. So 1 over mj, which is the fraction, that's what that limit is going to be positive. But the last one is another maybe, because if you start in state 7, that's the big infinite recurrence class, it might happen. This was the only reference to no recurrence on the whole exam. I figured I could give you one problem that had like 1.5 points of no recurrence, even though we didn't do hardly anything about it. If that's a null recurrence class, then that limit is 0. And if it's a positively recurrence class, current class, that number is finite and non-zero. Robert.
I had a question about the previous one.
Yep.
So when you say that mj n over n,
Uh-huh.
that's the state where it's starting, right?
Right.
So couldn't it be that if you start in different states, you converge to different numbers?
Yes, absolutely.
So although you converge to different numbers, it's still considered like converge.
Yeah, it can, no matter where you start, it converges to something.
But it converges to different.
Yes, absolutely. It converges to different things depending on where you start. You may never hit 7, right? But the point is, with probability 1, that limit exists. It equals different things depending on where you start, yeah. So maybe you were thinking, yeah, I think maybe some people got that wrong. We're thinking there's a single limit that converges to with probability 1. Yeah. Okay, well, anyway,
Sorry, Professor.
any other, Matt? Yep.
Yeah. On the last bullet, I don't get how the second recurrence class could not be null recurrent.
You can have an infinite positively recurrent class.
Okay.
Yeah, some of those examples in the pictures that go with the Markov chain handout. I say, if you change the values on these arrows, you can make it that they're all transient states, or they're all null recurrent states, or they're all positively recurrent states.
Okay.
Randy.
I have a question on the second one. So the second one is the true false.
Yep.
So is that the expected number of times you'll hit state 11 started, assuming you start in state 1?
Yes.
So how's that infinite if there's a chance that you'll end up in the other recurrence?
It's infinite with positive probability, and therefore the expected value of n11 is infinite with positive probability. Therefore, the expected value starting from 1 of n11 is, yeah, infinite. Yeah. So there's a difference between expected value and actual thing. Yep, Muhammad.
Or again, I don't understand why the last bullet in 7 is maybe, right?
Yes.
Why? Isn't this class a null recurrent class?
No, it could be a positively recurrent class. It's an infinite recurrence class, but it's possible to have an infinite recurrence class be positively recurrent. Yeah, in fact, that's the generic situation. Okay? Yeah.
So how do you distinguish between a null recurrent and a positive recurrent if
You have to compute what its MJ is, or its limit, the definition of it, the FKIJs and all that stuff. Yeah. It's if EJ of TJ equals infinity, then it's a null recurrent state. If EJ of TJ is finite, then it's a positive recurrent state. Yeah.
Is it possible to have infinite recurrence class where every element is null recurrent?
The only way that you can have a null recurrent state is in an infinite recurrence class.
Yeah, but is it possible that all of them be null
They all have to be either null recurrent or they all have to be positively recurrent. That's one of the rules about recurrence classes. So you can talk unambiguously about a concept like a positively recurrent class. Okay, I didn't compute any stats on this test yet. If you know, I'll figure out the mean, but I don't use that in any meaningful way. So, you know, I would say, you know, unless you got like below 60, I wouldn't worry too much about it, you know. But no, actually, no one should worry about like getting an unusable grade in this class. No one. But some people did very, very well, and you know, some people got messed up by one thing, you know, and I don't know. So you know, if you have any questions, let me know. Okay. Any other general things? All right. Yeah. Yep.
Are we back to the lesson or no?
Yeah, we're back. We're back.
So about this Lysis theorem, is that what it's saying is that if the next generation is good in terms of fitness, then it will keep on getting better every subsequent generation, and if it's worse, it's going to get worse?
Well, it's more like canonical observable for price is something like height, weight, you know, wingspan, you know, feather color averaged over the grayscales. I don't know. Those are the kind of things he was thinking of, right? But we're thinking of using it for average fitness in a GA design problem. Okay.
So it's basically working on the phenotype space.
Well, what you're see, the thing is that the way that parents give rise to children only has to do with the encoding and the genetic operators. Okay? We don't care what those guys encode, but if you happen to design the encoding so that by virtue of using these genetic operators, you have a high positive correlation between the average fitness of the parents and the average fitness of the children, then maybe that'll make the GA work better. That was my point. Yeah. It's an unanswered question whether that's true. I mean, that's an idea, you know. Whatever. Okay. Any other questions anybody have about this before we move on to the, or spend our last 10 minutes today, 11 minutes? Okay. Good. So anyway, as I said last time, the inertia associated with these monomorphic populations in GA is in some sense an artifact of the fact that you're using an exogenous fitness function. Okay, so remember, can't use recall in the middle of the class, that the sort of inertia of, ouch, severe foot cramp. Where did that come from? All right. The inertia of the monomorphic populations in the fitness proportional selectional GAs was sort of an artifact of the exogenous nature of the fitness function. It's coming from the outside. And when I say it's, ouch, it's an artifact of those things, what I mean is that in biology, monomorphic populations are not fit because the fitness is endogenous. So in biology, monomorphic populations aren't fit because, among other things, the fitness of an individual depends not only on that individual, but on who else is there. So these are because of obvious reasons. And in fact, biological fitness of an individual depends not just on traits of the individual, but on who else is in the population, who else is around. Okay? And you might remember back the first week of school, I told you, a classic game that people talk about is scissors, paper, rock. I have the idiosyncratic way of naming it that you guys don't like. Okay, anyway, but the point is that if I'm a scissors, right, and the population is full of papers, then I'm a fit individual. But if the population is full of rocks, I'm not, right? That's the whole point. So you can't really sort of say, how fit is a scissors independently of what population it inhabits? And that's something that GAs, as we've talked about so far, which have sort of been hijacked by the function optimizing people, don't really let us talk about. They let us only talk about the maximizing exogenous fitness functions. So what we need is, if we want to study processes where fitness of individual depends not just on its traits, but on who else is around and what they're doing, we need a mathematical tool that encompasses that kind of a situation. And that's what game theory gives us, and in particular, evolutionary game theory. Okay, so game theory is the appropriate math tool for studying problems where how well an individual does depends. And by the way, one of the sort of kind of cliche whatever features of game theory, if you pick up a game theory book, they always have some clever way of using gender-neutral language to talk about players of a game. They like some books will say in even-numbered chapters all the players will be male, and in odd-numbered chapters they'll be female, or all the even-numbered players will be male and all the odd-numbered players will be female, or something like that. But I try to use things like an individual when I can. But anyway, how well an individual depends not just on what he or she what they does. Yeah, but then it might be construed as one of those, reclaiming the plural pronoun, right? No, some people, like transgender people, like prefer to be called they and them. Yeah. There's a columnist for The Sun, actually, that says, it says in the her, or it's there. I don't know. Preferred pronoun, they, there. He or she does, but also on what everybody else does. That's what game theory is for. And as we'll see, evolutionary game theory is just this thing kind of on steroids, where you're evolving populations of agents that are doing things and doing well or doing badly, depending not just on what they're doing, but on what everyone else is doing. Okay? So that's what game theory is all about. And what is a game? What is a game? 2048. Okay. Well, why don't we, like, it's stupid to start this today, especially when I'm sort of half zombie sickness. So let's just pick it up next time, rather than say a finite game consists of n players, blah, 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 All right.